Hello everyone. So in this pre-lecture we're going to get down to the business of solving the Schrodinger equation, or at least taking steps in that direction. I've written here the Schrodinger equation for the wave function psi, which is a function of position x and time t. On the left side of the equation you see I h bar times the time derivative of that function. On the right side we see some constants times the second derivative with respect to x of the wave function. Plus v, which is the potential energy of the particle, specifies these sort of conditions that the particle finds itself in, or in the language of classical mechanics, it's the related to the forces, quote-unquote forces, that the particle is experiencing. We want to try to solve this equation. This is a partial differential equation. I've got partial derivative with respect to time on the left side, partial derivative with respect to x on the right side, and we want to know what is the function psi. The bad news is you can't solve this in general because I need to specify what this potential is. I can't solve it for an arbitrary potential. So a lot of our games in this class are going to be specify a particular potential and then try to solve this partial differential equation. I'm going to make a simplifying assumption. We're going to assume that the potential V depends only on x. It doesn't depend on time. What this means is that if you want to go back to forces, basically the forces that the particle is experiencing are not changing with time. So for example, imagine a classical particle feeling a gravitational force. The potential energy is mgy. That doesn't depend explicitly on time as long as g, the gravitational field, doesn't depend on time. If I go back to classical mechanics, I have a mass on a spring. The potential energy is 1/2 kx squared. It also doesn't depend on time. So actually this isn't that limiting of an assumption. As long as the main landscape or conditions the particle finds itself in are not changing with time, we can still make a lot of progress. And the first line of attack when you're attacking a partial differential equation is this trick called separation of variables. So we're going to use this technique called separation of variables. And you've probably learned that when you're solving a differential equation, you a lot of times have to make a guess as to what you think the solution is going to be. And this is exactly that. It's a particular guess. And why do we guess this? Well, it just turns out that 150 years ago when people were working on solving differential equations, they tried a whole bunch of guesses, and this is one that worked sometimes. So that's why we use this one. So here's the guess. You're going to guess that the wave function, psi is a function of x and t, factorizes into two different functions. We're going to call the right side small psi, which is a function of x only, times another function phi, which depends only on t. So I'm assuming that the dependence on x and t factorizes into two separate functions. The full wave function capital psi is the product of two functions, small psi, which depends on position, and phi, which depends on time. And what we have to do now is plug this in and see what happens. Before I get too far, let's introduce some notation. The notation of the dot is going to be the derivative with respect to time. And I'm going to use the notation as the prime is going to be the derivative with respect to x, partial derivative with respect to x. So capital psi dot is the derivative with respect to time of, using our guess now, psi of x, phi of t, which is, of course, just equal to psi times phi dot, because psi doesn't depend on time. Right? The other derivative that appears in the Schrodinger equation is d psi dx squared. So that's capital psi double prime, derivative with respect to x. That's going to be the second derivative with respect to x of psi of x, phi of t, which is going to be psi double prime times phi. So let's plug all of that in to the equation above. And on the left side we have IH bar, d psi dt, which is just this psi of x, phi dot of t, right? And on the right side, I've got this minus h bar squared over 2m. The second derivative of psi with respect to x squared, which is this, so that's psi double prime of x phi of t. And then we've got this last term here, which is plus v of x, psi of x, phi of t. Okay. And it doesn't look like it's accomplished too much. It looks kind of like it's just made things more complicated, but we'll see why that's useful in just 1 second. All right, the next step is I'm going to divide both sides by psi of x times phi of t. So I just divided both sides by the same thing. And what do we get here? We see there's some cancellation. So this psi on the top here cancels with that psi. This phi here cancels with this phi. And both the psi and the phi here cancel with each other. And let's rewrite it and see what we have. All right. Let me clean this up a little bit. So taking a look at what we have now, we see that the left side of this equation depends only on time, and the right side of this equation depends only on x. So we have here manipulated our Schrodinger equation, our partial differential equation, into a form where all of the time dependence appears on the left side of the equal sign, and all of the x dependence appears on the right side of the equal sign. And so you're still kind of asking, what is the point of that? Why is that useful? So let's think a little bit carefully about this. So if I think about the left side of this equation, it does not depend on x, right? By assumption, it does not depend on x. But the left side must be equal to the right side. There's an equal sign here. And the right side does not depend on t, right? So if the left side is equal to the right side, and the right side doesn't depend on t, then the left side must also not depend on t. If it's too fast, see if you can work it out for yourself. But we assumed something so that the left side doesn't depend on position. But the left side has to be equal to the right side, which doesn't depend on time. And the only way that's possible is if the left side also doesn't depend on time. So how do we get out of this debacle? It seems like it does depend on t, but it doesn't depend on t. So there's only one way out of this, is that the left side must be a constant, c. Let's call it c. Because it can't depend on t, and it can't depend on x because of that argument, so it must be a constant. But the left side's equal to the right side. That means the right side must also be equal to that same constant. So this is equal to c, and this is equal to c. Both sides are equal to a constant. This is called separation of variables. For obvious reasons, I got all of the t dependence on the left side, all of the x dependence on the right side. Anytime you have this situation where you have all the dependence on one variable on one side, all of the dependence on another variable on the other side of the equal sign, it must be the case that both of those sides are separately equal to a constant. We have actually reduced our partial differential equation into two ordinary differential equations. One is this equation, I h bar phi dot over phi is equal to a constant. And one is this equation, minus h bar squared over 2m psi double prime over psi plus v is also equal to a constant. So we've separated our partial differential equation into two ordinary differential equations. And let me write those ordinary differential equations down for you. Okay, so you're like, well, great. I mean, we started with one equation, now we've got, what's the purpose of that? The nice thing here is that these are ordinary differential equations. They're not partial differential equations, right? This is an ordinary differential equation for the function phi of t. It's a first order differential equation. And this is a second order differential equation for the function psi of x. And the good news is, like, it's easier to solve ordinary differential equations than partial differential equations. So we have now two ordinary differential equations that we have to solve. If I can solve this equation for phi and this equation for psi, I can multiply them together, because remember, my full wave function, which is what I want, is just the product of those two, phi of t and psi of x. Basically going to wind up here, except I want to do one more thing, which is I want to think a little bit more about this constant c. So what I've written here are the two equations that we found earlier, the two ordinary differential equations. And you have a constant c which is showing up here, and it seems like this abstract constant, but if you ever want to learn about something, it's always a good question to ask, like, what are the units of that thing? So based on the structure of these equations, can you tell me what are the units of the constant c? I'm going to go ahead and ask you to pause the video. Maybe you can take a look at it, think about it for a second. Among these choices here, can you determine what are the units of the constant c? All right. So have you made your choice? Let's think carefully about it. C appears in both equations. I could use either one. So if I look at the top equation, I've got the units of h bar, the square brackets mean units, times the units of d phi dt, divided by the units of phi, are equal to the units of c. Right? Now the units of d phi dt are the units of phi over the units of t. So the units of h bar times the units of phi divided by the units of t times 1 over the units of phi are equal to the units of c. And so I get the units of c are the units of h bar divided by the units of time. What are the units of h bar? It has units of angular momentum. That's joule seconds divided by seconds. So the units of c are joules. Right? So the constant c is going to be interpreted as some energy. Instead of c, let's call it E, because we know it has dimensions of energy, so it's some kind of energy. So that gives us these two equations, I h bar phi dot over phi is equal to E. And we have this equation minus h bar squared over 2m psi double prime of x over psi plus v is equal to E. Let me just recap what we did. We started with the full Schrodinger equation. We made an assumption that the wave function psi of x and t is psi of x times phi of t. That's called separation of variables. We also assumed that v of x and t only depends on x. And with those assumptions, we plugged them back in. We did this argument about separation of variables. We got two ordinary differential equations. And to make further progress, we have to start solving those ordinary differential equations. I hope you found this useful. Thank you again for your attention, and I will see you all in class. Bye for now.